Previously, we have introduced the definition of a function in terms of binary relations. Recall that a function from set A to set B is basically a binary relation from A to B, which is both entire and functional. In this section, we will turn to many examples to further illustrate this definition. Many of the examples mentioned in this section will be frequently encountered in the rest of our course. Our first example is the constant function. Assume that we're given two sets, a set A and a set B. Moreover, let us fix an element b star in set B. Now we can define a function denoted by fb star from set A to set B, where all elements in A are sent indifferently to the element b star in B. Since the function value is unchanged regardless of the variable x in the domain, we call this function a constant function. And the constant function is probably one of the simplest functions that we can imagine. Our second example deals with the indicator function. To this end, let A be a non-empty set and S be a subset of A. We construct the function from A to a set consisting of only two elements, namely 0 and 1, such that for every element x in A, if x is in S, then we send x to 1. Otherwise, x is in a complement of S in A, and in this case, we send it to 0. We call it an indicator function. By defining such a function, we have delivered a label, either 0 or 1, to each element in the set A. And such labels indicate if a given element belongs to S or not. For instance, the Dirichlet function, which sends each rational number to 1 and each irrational number to 0, falls into this category and can indeed be seen as an indicator function. Now let us study some examples which connect a product set A cross B to its components. To this end, let A and B be two non-empty sets. First, we construct a function from A cross B to A, which sends each ordered pair xy in A cross B to its first coordinate, that is, x. We often call it a projection. On the other hand, we can construct a function from A to the product set A cross B as well. For example, we can first pick an element, namely y star in B, and we fix this element once and for all. From there, we can construct a function, namely I y star, which sends each element x in A to the ordered pair x y star in A cross B. We have used the notation I y star to emphasize the dependence of this function on the choice of that fixed element in B. These functions permit us to transform between a product set and its components. In our next example, we assume that A is a non-empty set and S is a non-empty subset of A. Now we can define a function called IS, whose domain is the set S, whose codomain is the set A, such that each element x in S is sent to X itself. Since S is a subset of A, if X belongs to S, then X belongs to A. Thus, this function is actually well defined. We call this function an inclusion map, under which set S is naturally included in set A. Our next example is called the evaluation map. Before its construction, let us first define a set, denoted by b to the power of A, which consists of all functions from A to B. Now, the domain of the evaluation map is the product set BA cross A, and the codomain is the set B. The correspondence takes place in the following way. For an ordered pair from this product space, that is, a function f from A to B, as well as an element x from set A. Now, since x belongs to A, which is the domain of our function f, we can apply f to x, which then evaluates to the element fx in B. This function permits us to study a family of functions sharing the same domain and codomain. Moreover, from this example, you can see that functions themselves can be inputs of other functions as well. Our last example concerns a function that is actually trivial, yet more or less counterintuitive. To this end, let us pick the domain A to be the empty set. In this case, no matter which codomain B we're going to take, the product set empty set cross B will always be the empty set itself. And the only subset of this product set, that is, the only binary relation of this product set, is the empty set as well. To see whether this defines a function, we only need to check if the empty set as a binary relation is entire and functional. Yet, recall the definition for these two properties are all quantified statements starting with the universal quantifier. In other words, when A itself is the empty set, these two properties are vacuously true. Thus, when set A is empty, we indeed have a trivial function which is the empty set itself. As a result, when the domain A is empty, there exists one and only one function from A to B. That is, the empty set itself.